So the first actual technique is the technique we've already seen, that being using substitution. But one of the big differences in extension 2 is you may not be given the substitution, but it's still a method you're allowed to use, of course, if you spot it and want to use it. Here are what I call the non-standard integrals. I only call them that because they're not on the reference sheet. But if you remember them, you're going to save some time because they do crop up a fair bit. Du on root u is 2 root u. Du on u squared is another very common one. Du on u squared is minus 1 on u. Log x is x log x minus x. Tan x log a sec, or minus the log of cos if you prefer. Then there's these three. Now they used to be on the reference sheet once upon a time, but they're not anymore. For some reason they took them off. They might give them to you, which is nice if they do. They might ask you to prove it, but if they don't do either, you can quote them. So sec tan goes to sec, and the bottom two there, look at them, they're very similar. The square root of x squared, now one's minus a squared, the other's plus a squared, but look at the answer. The answer also is very similar. Basically they're the same, you just match the square root sign. So log of x plus the square root sign, or whatever was in the question itself. You'll notice it says x is bigger than a is bigger than 0. You need that on that one because otherwise x squared minus a squared would be a negative number and you can't find the square root of a negative number. So x, square root of x squared plus 4, they haven't given me the substitution. So say I wanted to do this by substitution, what would I do? Well, the first idea I might try is whatever's causing the problem, I'll make the substitution. And that's usually what's in the square root sign. So let's make u equal to x squared plus 4. So there it is, there's u. And then du is 2x dx. So we've got half of our du there. So we end up with the integral, or half the integral, of u to the power of a half. Add 1 to the power over the power. Sub back in for u. Mere mortal answer. Super mathematician. 1/3 x squared plus 4 root x squared plus 4. That's one way we could approach this one. Another way I might have looked at it, I might have looked at this and said, well, hang on, when I've got a square root of a sum of 2 squares, sometimes a trig substitution is handy to use. So let's try it with a trig substitution. What I want to do is turn it into one of our trig identities, because then we can get those 2 terms under the square root sign and turn it into one thing. So if I make x equal to 2 tan theta, so dx would then be 2 sec squared theta to theta, we would end up with, okay, so x is 2 tan theta. Under the square root sign, we now have 4 tan squared plus 4, which is, of course, 4 sec squared. But the square root of 4 sec squared would be 2 sec. So, and then, don't forget the dx is 2 sec squared. Multiplying all of that together, then we've got 2 times 2 times 2, which is 8. We've got a tan theta. We've got a sec times a sec squared. So we end up with sec cubed. Now, have I made life any easier for myself? Well, turn everything into sine and cos because I can't see right away what this is going to do. So I've now got sine theta on cos to the power of 4. All right, well, maybe I'll do another substitution. Let's let u equal cos theta. Then du is minus sine theta to theta. So I get minus 8 du on u to the power of 4. I finally got something I can integrate. So add 1 to the power over the power, but u was sec theta, so I can get the sec theta back in there, but I've still got to get it back to the x. Now, how on earth do I get x back into this? X was 2 tan theta. So I draw myself up a little triangle. If x was 2 tan theta, that's the same as saying tan theta was x on 2. So opposite over adjacent. Hypotenuse, not a coincidence, it will turn out to be the square root. So now I can sub back in. Sec theta, sec is reciprocal to cos, so it would be hypotenuse over adjacent. So hypotenuse over adjacent gives us the square root of x squared plus 4 cubed over 8, but it cancels with the 8 we already have. We end up with 1/3 the square root of x squared plus 4 cubed, and then we finally get the same answer. Now, I'm not saying that's the best way of doing that one, but you could if you wanted to. Of course, the easiest way of doing this problem was if we just looked at the question and saw straight away that we've got, derivative times the function. And that, of course, would have been the quickest and most efficient way of doing this question. But let's have a look at this one. X root x plus 1. Well, I'm going to let u equal the whole of the square root sign this time. That's an alternative. Instead of making it what's in the square root sign, make it the whole of the square root sign. But then you'll notice I rearranged it and made x equal u squared minus 1. And I'll do a straight substitution in for the x's and the dx's. So we get u squared minus 1, u times 2 du, u to the power of 4 minus u squared. So add 1 to the power over the power. Now I can sub my u back in. Mere mortal. Look at that beautiful answer. Once we do some factorising and everything. Of course, another way I could have done that one. I could manipulate the algebra out the front. And so I'm going to rewrite that as x plus 1 minus 1. Because then I can write it now as two things. I've got x plus 1 to the power of 3 on 2 minus x plus 1 to the half. They're linear functions to a power, so I can just add 1 to the power over the power, and we get to where we were before. Another way we could have approached that one. Dx over 1 plus root x all squared, and also times the square root of x. 1 plus root x is in the parentheses there, so I'll give that a go. Let's see what happens. 1 plus root x, differentiate it, I get dx on 2 root x, okay? But, got to do the limits as well. So when x equals 1, u equals 2, x equals 4, u equals 3. All of that just tidies up to be 2 times the integral from 2 to 3 of du on u squared. It's important that you separate your variables before substituting. Now what that means is you don't do this sort of thing, which I have seen. Some people substitute in dx equals 2 root x du and then go, oh, but it's all right because the root x's cancel. No. We always separate the variables out. You don't have an integral with mixed variables in it. So if your new integral is du, your limits must also be with respect to u. So we've mentioned that before as well. It's a complete substitution. There should be no mention of x in our integral. So du on u squared, as I say, that's minus 1 on u. Sub in the 3, sub in the 2, we get a third. There's a trig one. Well, with this one, again, I look at it and I'm just looking at derivative times something to a function myself. But if I did it by substitution, well, sine's to the power of 5, so it's the logical one. U equals sine x, du is cos x. Fix up the limits. So we're just integrating u to the power of 5. 1 to the power over the power. Sub in the 1, sub in the root 3 on 2. And we end up with 37 on 384. X dx on the square root of 25 minus x squared. Again, and hopefully you're getting to this point as well where you see that straight away and you can say, oh, look, on the top's the derivative of the functions on the bottom. But if we didn't, then I go, okay, what's causing the problem? U is 25 minus x squared, so du is minus 2x dx. Change our limits, sub in. There's that du on root u again, which we know is 2 root u. So half times the 2, we end up with root u. But notice I've swapped the limits around and got rid of the negative sign on that one. Root 16 minus root 9 is 1. Square root of 25 minus x squared. Now in this case, I can't do 25 minus x squared because I won't have the dx part there. It's missing. So I'm going to turn it into a trig identity. So I'll make it x equals 5 sine u. Another way of thinking about that is u equals the inverse sine of x on 5. But dx will be 5 cos u du. The limits, and that's why I think I rearranged to make it u equals the inverse sine, so I could work out these limits a bit easier. So when x is 0, u is 0, and when x is 5, u is pi on 2. So 25 minus 25 sine squared would be 25 cos squared. Square root of 25 cos squared would be 5 cos. Times it by the other 5 cos, and we now have 25 cos squared. But when we integrate cos squared, we use our double angles. So that'll be a half of 1 plus cos 2u. Integrate that. Fortunately, we don't have to substitute back in because it's a definite one. I can just put these numbers in. And there we go. 25 pi on 4 as our answer. Of course, another way of doing it. Square root of 25 minus x squared. Hang on a sec. I know what that shape is. That's a semicircle. Or rather, it's a quarter because I'm only going from 0 to 5. So it's just that bit in there I'm trying to find. Well, I've got a formula that finds the area of a circle. 25 pi on 4. A heck of a lot quicker. So again, if you recognise the shape, use it to your advantage. So 4C, and as I say, you're not necessarily going to be given the substitution to use in extension 2.